Ask for the optimal satellite height, and the honest answer begins with another question. Optimal for what? Imagine a ship near a growing storm, cut off from the satellite systems that normally protect it. This is an accelerated thought experiment, not a real-time launch plan. We need three things: a clear view of the danger, a reliable position, and a warning link. If one altitude were perfect, every replacement would belong there, but detail, coverage, delay, lifetime, and energy pull in different directions. The rescue has to be built in layers. Chapter 1. The Eye. The first job is to see the danger clearly. That points toward low Earth orbit, the region below roughly 2,000 kilometers. At about 550 kilometers, an observation satellite remains close to the planet. For an identical imaging instrument, less distance means finer ground detail. Storm structure becomes easier to measure and track. The shorter distance also helps radio links. Signals spend less time traveling, and reaching the orbit requires less launch energy. For detailed observation and low delay, closeness is extremely valuable. But closeness does not let a satellite hover. Orbit is a continuous fall. Gravity bends the spacecraft downward, while sideways speed carries it beyond the curved horizon. It keeps missing Earth. At this height, that sideways speed is about 7.6 kilometers per second. One journey around Earth takes roughly 95 minutes. Any particular region remains available for only part of that orbit. Continuous observation therefore needs a constellation. One satellite hands the job to another as each disappears beyond the horizon. The system trades one permanent watcher for a coordinated chain of moving ones. Low orbit also passes through traces of the upper atmosphere. That thin gas creates drag and slowly removes orbital energy. Working spacecraft may need occasional reboosts to maintain their height. The same drag can help clean the orbit. Below roughly 600 kilometers, it can often return uncontrolled hardware within years. Farther up, abandoned objects may remain for centuries or longer. Low orbit is an excellent eye. It provides detail, short signal paths, and relatively easy access. It also brings motion, handoffs, drag, and limited time over one place. That restores the weather picture. Low orbit could also host a communications network. Our first layer was designed for observation. Navigation is a different job, and it needs a different design. Chapter 2. The Compass. To restore position, move into medium Earth orbit. The GPS satellites use an altitude of about 20,200 kilometers. Each one circles Earth roughly twice per day. GPS works because of geometry, not because the middle altitude is magically balanced. Its baseline design uses 24 orbital slots arranged across 6 planes. That arrangement keeps several satellites spread across the sky. Each satellite broadcasts its own position and a precise transmit time. A receiver compares those signals with the time they arrive. The tiny differences reveal the receiver's distance from each satellite. Signals from at least 4 satellites solve the full navigation problem. 3 coordinates locate the receiver in space. A 4th measurement corrects the receiver's imperfect clock. The position is calculated inside the receiver. It does not ask the satellites where it is. GPS is fundamentally a one-way timing service, not an ordinary two-way conversation. That is a property of GPS, not medium orbit itself. That distinction matters to our rescue. Navigation can tell the ship where it is. It cannot, by itself, deliver a live warning from shore. Medium altitude gives each navigation satellite a broad reach and predictable geometry, but its signals travel farther than low-orbit signals. The spacecraft also require more launch energy. Radiation is another cost. Parts of medium Earth orbit cross a harsh radiation environment. Electronics, shielding, and mission lifetime must be designed around that exposure. The middle road is not a compromise-free gap. It is a deliberate trade chosen for navigation. We now know the danger and the ship's position. One problem remains: keeping contact. Chapter 3. The Lighthouse. A continuous regional link benefits from a satellite that stays in the same part of the sky. That leads to geostationary orbit. The conditions are exact. The orbit must be circular, equatorial, untilted, and moving eastward. Its altitude must be 35,786 kilometers. One orbit takes 23 hours, 56 minutes, and 4 seconds. That matches Earth's rotation relative to the stars. The satellite therefore remains above the same longitude. It is not parked. It still travels at about 3 kilometers per second and falls continuously around Earth. Its motion simply keeps pace with the turning planet below. That apparent stillness is enormously useful. A ground antenna can point in one direction and stay there. One satellite can maintain service across a broad region without constant handoffs. For broadcasting, regional weather monitoring, and long-distance communication, that persistence can matter more than closeness. It can keep shore and ship inside the same relay system. Distance still sends a bill. One ground to geostationary to ground hop has a minimum propagation time near 0.24 seconds. A request and reply exchange starts near 0.48 seconds. Real paths, processing, and routing add even more delay. This is not slow electronics. It is the unavoidable time needed for a signal to cross an enormous distance. The same distance reduces imaging detail for an identical instrument. High latitudes sit low on the horizon, and the poles are out of view. Reaching the orbit also demands more energy. Geostationary orbit is not better because it is higher. It is better when continuous regional presence matters more than low delay, fine detail, or polar coverage. Our rescue did not need one perfect satellite. It needed a system. Low orbit became the eye. Medium orbit became the compass. Geostationary orbit became the lighthouse. That is why the question has no single numerical answer. Earth imaging and low delay links often favor low orbit. Global navigation systems use carefully arranged middle constellations. Continuous regional broadcasting can favor the geostationary ring. Other missions choose different inclinations or stretched elliptical paths. Height is only one part of an orbit's address. Payload, coverage, lifetime, radiation, disposal, and cost all matter too. The optimal orbit is the one whose compromises fit the mission. The next satellite crossing your night sky is not sitting at the best height. It is a compromise made visible.